Okay, so today we are taking a look at electrochemical cells, galvanic and electrolytic cells. Electrochemical cells are the driving force behind things like batteries and electroplating. We have two notes. We have the Microsoft Word document, and we have a PDF of the notes. If you are working on a tablet and you're, scribbling on a tablet, I recommend the PDF. We're also going to need the relative strengths of oxidizing and reducing agents. That's this picture here. So you can either look off of this picture or you can download the document if you want. Thing to over here. So we're going to start with our note on galvanic cells. A galvanic cell is a device that converts chemical energy from redox reactions into electrical energy. Right, that's important. There. Okay. So, in this picture, I have a picture of what a battery sort of looks like inside, or how you could make a battery in a chemistry lab anyway. Okay, so we have, we'll just look over here. We have a piece of zinc metal on this side right here, and we have a piece of copper metal. And then we have two containers, glass containers, and we have a part of the metal is immersed in some sort of solution with ions in it, right? And the zinc metal also has its own solution. The zinc and the zinc and the copper metal are connected by a wire, okay, that electrons can flow through, and there is also a little tube full of salt called a salt bridge that connects them. So that is kind of, if you were asked to make a battery in a chemistry lab, that's what you could do. Okay, so in this battery, we have a chemical reaction going on, a redox reaction. Okay, and the redox reaction is right here. Okay, so it says that zinc metal, solid zinc metal, right? So the solid one is, the solid one is our metal, right? Plus a copper ion, because it has the charge there, makes copper metal and a zinc ion. Okay, this is a redox reaction. It says copper ions remove 2 electrons from zinc atoms, and the following changes occur. Right? So, okay, so we have basically we have an atom of zinc, right? And zinc will have 2 electrons somewhere on the outside, right? And we'll have a copper +2 ion. So what's going to happen is the electrons are going to jump from the zinc atom to the copper ion, right? And then, zinc, because it's now losing 2 electrons, will become an ion. And copper, because it's gained 2 electrons, right? We'll show the electrons here, is going to be an atom. So whenever something is an atom, it's solid, right? So we think of most metals as being solid, right? So, maybe some of you are wearing jewelry right now, and that's a solid um, metal. But when things become an ion, they dissolve, right? So if we could make redox happen with your jewelry, right, we could turn it into an ion, and then it would be soluble in water, which, I mean, most people don't want that to happen with their rings. Um, but if you have some gold and you want to hide it, you can dissolve it, and people won't be looking for your dissolved gold. They'd be looking for your jewelry instead. That's how uh, people hid their valuables in like World War II, right? They had their jewelry dissolved in a solution, and then afterwards they were able to get back the gold, not in a ring shape, but in a chunk that they could turn back into a ring. So after the reaction, zinc is a metal ion, right, which means it's dissolved, and copper is a metal atom, which is solid. So what's happening over time, okay, is undo? No undo. There's an undo. Okay. What's happening over time, right, is this zinc metal is going to wear away, right? It's going to turn into ions and it's going to dissolve. So this piece of zinc metal will dissolve, and this piece of copper metal will actually get thicker over time. Okay, so we can use this chemical reaction to make copper, but that's not why we do this chemical reaction. So because zinc loses 2 electrons, right? When you lose electrons, this is oxidation, right? So you can remember that this, you know, oxidation is loss, right? That's the oil in oil rig. And you can remember, so copper gains 2 electrons, right? And that's reduction. So oxidation is lost, reduction is gain. Right? And that's the rig part of the oil rig. Okay? So in this chemical reaction, copper is going to become reduced, and you're going to see it sort of the piece of metal build over time. And zinc is oxidized, and you're going to see it sort of erode. Right? That's what erosion is. It's oxidation. Okay, so if the oxidation happens on a cliff, right, that's like the sort of erosion that you'd see in geology. Or it can happen to metal, right? We call that usually corrosion. Corrosion is, the metal that rusts over time. So a galvanic cell is created if the zinc metal and the solution containing the copper ions are separated. So what happens is, okay, at the zinc piece of metal, it loses electrons, okay? And at the copper piece of metal, it gains electrons. So if you separate what's happening at the zinc metal with what's happening at the copper metal by a wire, the electrons will travel through the wire. And when electrons travel through a wire, you get electricity. So we do this reaction to generate electricity. So we have a redox reaction, right? Or 2 half reactions that are separated by a wire. And we force the electrons to go from one reaction to the other reaction through the wire. And we can use that to make moving electrons, which will create energy. So electrochemistry, right, can be used to create energy. And probably if you're watching this on a device and your device is not plugged in, that sort of chemical reaction is what's powering, you know, this class right now. I have my little tablet today, and you can see there. You can see the battery 70% of the way full, and something like this is going on inside of my iPad. So, um, okay, so we have to talk about this battery and the parts of the battery, and what they do. So, one thing to note is that in galvanic cells, in galvanic cells, reactions are spontaneous reactions, right? They require no outside energy to make them occur. Of course not, right? Because if you needed energy to make your battery run, it wouldn't be a very good battery. Batteries are supposed to uh, give us energy, not take energy from us. So we have to create our batteries, okay, so that um, so that the reactions are spontaneous, so that when we want to use our device, right, we complete the circuit and electricity will flow and we will have power. So let's talk about the different parts of a battery. Okay, those are on the next page. We're going to skip over the galvanic cell notation, and we're going to talk about the parts of the galvanic cell. So the first part that we have to talk about are half cells. Okay, they're separate compartments in which oxidation reaction and the reduction reactions occur. Each contains an electrode, which is a solid piece of metal, a solid conductor, and electron transfer occurs between the atoms on the surface of the electrode and ions in the solution. So, okay, so the two containers are each a half cell. Right? So we have two half cells. And each half cell contains a half reaction, right? It contains half of the redox reaction. So one part of the redox reaction is the zinc going from zinc metal to zinc ions and giving up electrons. And the other half reaction is going from copper ions to solid copper, and it's taking in electrons. Okay, so the electrons from the zinc half cell are traveling through the wire, and they're running the copper half cell. The We have the two pieces of metal. Those are called electrodes. And we have two types of electrodes. We have something called an anode and something called a cathode. Okay, the way that you can tell the anode from the cathode is by what type of redox reaction is going on in its half cell. So at the anode is where the oxidation takes place. And at the cathode, that's the place where the reduction takes place. Right? So there are two electrodes, and you can figure out before you run the battery which one is going to be oxidized and which one's going to be reduced. Right? And that goes back a little bit to our predicting redox reactions lesson. So if you remember, we had those reduction potentials, right? And those reduction potentials, reduction potential, I didn't call it. The chart with the strong and the weak reducing agents and the strong and the weak oxidizing agents, right? If you find zinc and copper on there, you're going to find that that zinc is a very good reducing agent, which means it's very good at being oxidized. Okay, and you're going to find copper is a very good oxidizing agent, which means it's very good at being reduced. So based on where it is on that table, and I'll show you in a little bit how that works. Actually, maybe I'll show you now. Okay, so we have zinc and copper. So if we look, there we go. If we look at zinc and copper, so copper is up here, and zinc is down here. Okay, so the bottom is for stronger reducing agents, right? And reducing agents are things that things that oxidize more easily. Right? So we can see that because zinc is towards the bottom, zinc will oxidize more easily. Okay? Copper is near the top. It's a weaker reducing agent, but its ions are strong oxidizing agents. So metal ions tend to want to oxidize. They tend to want to steal electrons from other things. And metal atoms tend to want to reduce. They want to lose electrons to things. So copper ions are the strongest reducing agent that we have in this electrochemical cell, right? We have basically four things that can react, okay? We have copper ions, we have zinc ions, we have copper, solid copper, like metallic copper, and we have metallic zinc, right? Of the two metals, zinc is closer to the bottom, so it's going to be our reducing agent, and it's going to oxidize. Of our two metal ions, copper 2 plus and zinc 2 plus, copper 2 plus is the stronger reducing agent, so it will reduce more easily. Right? So things that are closest to the bottom will become our anode, and things that are closer to the top will become our cathode. Okay, so that's how you can choose an anode and a cathode if you're given two metals, because sometimes we just give you two metals and you have to make a battery out of them. So that's how you choose which one will be the anode and which one will be the cathode. Okay, so going back, those are the half cells. Okay, so half cells, let's just re-review. Half cells are separate compartments, so separate containers, in which the oxidation reaction and the reduction reaction occurs. Each contains an electrode, which is a piece of metal, which is solid, and the electron transfer occurs between the atoms on the surface of the electrode and the ions in the solution. We have our anode. The anode is where oxidation occurs. We have the cathode. That is the electrode where reduction occurs. And we have a salt bridge that we haven't really talked about. So a salt bridge is a container of electrolyte solution, right? So it has an ionic compound. Right? So it's a source of ions. Its purpose is to prevent charge buildup from occurring and keeping the solution around each electrode neutral. So let's go back and look at what's happening at this electrode. Okay, so here we have an electrode. I'm just going to get rid of some of this. There we go. Okay, so what's happening at this electrode? It says that zinc, solid zinc, is turning into, right? I'm looking at the equation right here. Solid zinc, right? So in other words, the metal, okay, is turning into zinc 2 plus ions and electrons. So you can see right here, we have this zinc, right? And this zinc is what the metal is made of, okay? And atoms on the outside of this zinc rod basically are breaking up and turning into zinc 2 plus ions, right? And when they turn into ions, they dissolve. So they move away from the metal and into the container, into the water, right? So they dissolve into the water. And the other thing that it will break up into is electrons, and the electrons are going to go up the electrode and into the wire. Okay, so over time, as this reaction happens not once, but hundreds and thousands of millions and millions of times, we are going to have a buildup of many of these zinc 2 plus ions in solution, right? This will happen a whole bunch of times, and then the zinc ions will build up, right? But this is going to create problems for us because as the zinc ions build up, it becomes sort of an equilibrium situation, right? If too much product builds up, it's going to shift the equilibrium the other way, unless we can neutralize the charge. So what's going to happen every time we add a zinc 2 plus ion is an SO4 2 minus ion, right, will come down from the salt bridge, and these guys will pair up, and it will sort of neutralize the positive charge, right? So ideally, you would want, as this reaction went on, more SO4 minus 2 minus ions to build up, right, to counteract the 2 plus ions, right? So for every Zn2 plus that's created, we want an SO4 2 minus for it to pair up with, right? So in the salt bridge, right, here's the salt bridge, we have sodium sulfate, okay? The sulfate is going to always go down when we make a new zinc 2 plus ion, right? Just so they can neutralize the charge. So for every plus thing, there's going to be a minus thing. And then the same idea with the other side. So on the other side, okay, what's happening is a little bit different. What's happening is the copper ions are picking up the 2 electrons and turning into solid copper, right? So as this reaction goes on over time, right, every time we do this reaction, we remove the copper 2 plus ions from the solution, and they become part of copper metal. So over time, we're going to deplete our stock of copper 2 plus ions. So what's going to happen is there's a little bit of sulfate. The sulfate is going to go up into the salt bridge. Okay, and sodium atoms will come down. So sodium atoms are positively charged like copper atoms, and they will build up over time, right, in the solution, which keeps it from becoming too negative. Okay, and eventually, though, some things will happen, and this battery will stop working. Okay, so the first thing that could happen to make this battery stop working is we could run out of ions in the salt bridge, right? And that will make the reactions, it will make the reactions happen more slowly. Or the second thing that we could happen is we could run out of zinc metal in our anode, and then the battery will stop working as well because we have no more zinc to turn into zinc 2 plus ions. So we can't do this half of the reaction, and that's when your battery dies. Okay, so that's the salt bridge. The salt bridge is a container of electrolyte solution, right? And it doesn't matter what it is, but it will always have two components, right? It will have a cation, which is a positive ion, okay, to replace the positive ions as they go away. And they'll have an anion, which is a negative ion. The cation is always the first thing. The anion is always the second thing, right? And the anion will go to the anode, and the cation will go to the cathode, right? So you can see sort of where they got their names from. Anyway, so the salt bridge connects the two solutions of the galvanic cell, and the purpose of it is to prevent the charge buildup from occurring and keep the solution around each electrode neutral. We can also describe a battery with something called galvanic cell notation. Okay, so we can describe this battery using this. So I could write this down and I could give it to a chemist and they could recreate the battery. So how does this work? So I would know as a chemist that everything before the double line in the middle is the anode. Okay, so in the anode, we write the electrode first. Right? The electrode is made of the solid metal. In this case, it's zinc metal. Okay, and then we have a single line. Right? This is not a capital I. This is on your keyboard. It's called a pipe, and it is located usually a few spaces over, a few keys over from the P on your keyboard. Usually it's somewhere around there. It's usually on a key, right, with the backslash. So they have the backslash on top and they have the pipe on the bottom, or the other way around, actually. Looks like that. So you can find that this is the pipe. So we have that pipe separates the electrode metal from the ion in the solution, right? And you can see the electrode will always be basically solid, and the ion will always be aqueous, right? So the double line is trying to reflect the salt bridge, okay? So it's going to separate the two containers. After the double line, we have the cathode half cell. So if you want to do, by the way, the salt bridge, right, it's just 2 pipes in a row. After the 2 lines, we have the cathode half cell. And you can see here we put the ion first and we put the electrode second. Right? And the way that we write the anode and the cathode half cell are backwards. They're backwards from each other because it shows sort of our reactants and our products. Right? So zinc starts out as a solid but becomes an ion, and copper starts out as an ion and becomes a solid. Right? And the electrons will always flow from left to right. They will always flow from the anode to the cathode. Okay, so that is galvanic cell notation. Sometimes people can't find the pipe key on their keyboard and they can use a slash instead. Yes. Yes. So the important thing also is to, in this, put the phase. Right? If something's solid, put an S beside it. If something is an ion, put an AQ beside it. Right?
May
And that's, yeah.
question.
Yeah.
Sorry. When in our exam and say we forget to put an S or a Q, do we get marks taken off?
If it's okay, if it's something that's really, really important to what you're doing, like if it's in a galvanic cell notation,
Mm-hmm.
because it is really, really important that you write the phase here, I would take it off for something like this, but I might not take it off for something where it's just not important, like where you're just balancing a chemical equation or something like that.
Okay.
Yeah, it's a good question. Try to be a fair marker, right? So I try not to take too many petty marks off exams and things like that. Because it's time limited, you know? Cell reactions. Okay. So it says the oxidation and reduction half reactions can be predicted using the activity series of metals. The activity series of metals is that sort of chart that I showed you. Okay. The metal higher in the activity series is oxidized and the lower is reduced. For us, in our chart, it's opposite, right? So the metal lower on the um lower on the what did they call it, standard reduction potentials, is oxidized, and the metal higher on the standard reduction potentials is reduced. Okay, so normally they give you two. If you took a course like this, they would give you the activity series and the standard reduction potentials, but we don't need that, right? So the we're going to use the standard reduction potentials, and the anode is always going to be the lower one, and the cathode is always going to be the higher one. right? In other words, the stronger reducing agent is your anode, and your strongest oxidizing agent is your cathode. So from this, right, we know that our anode, which is the zinc in this case, is going to be oxidized, which means the metal is going to lose electrons and form an ion, right? So if electrons are a product, it means that they are lost. In the cathode half reaction, you can see that the electrons are a reactant, right? So that shows that they are gained. Atoms from the zinc electrode lose electrons and dissolve as Zn2 plus ions in the zinc half cell. Copper ions, which are aqueous, dissolved in water, in the copper half cell gain electrons and become neutral copper atoms, and they deposit on the copper electrode. Okay, and it says, therefore, as the cell operates, okay, this is a very important part, as the cell operates, the mass of the zinc electrode decreases and the mass of the copper electrode increases. Okay, the overall cell reaction can be obtained by adding the half reactions together. So if you add the anode half reaction and the cathode half reaction, you can see, because we have the same number of electrons on the product side and the reactant side, they cancel out. Okay. During the full reaction, anything before the arrow ends up on the reactant side, right? And anything after the arrow in both equations ends on the product side. Okay, we can also, when we write down the anode and cathode half reactions, we can look up their electrical potential. Okay, the electrical potential is how much energy we get from running the half reactions. Okay, and if we run the half reactions together, we can get a total potential or total energy, right? So if we have a zinc copper battery, which we do a lot, you go to the dollar store and you buy like a battery for your remote control, you can buy like a Duracell battery. And Duracell batteries, you ever notice they have they're black, but the top of them is sort of a copper color? Well, that's because it's a zinc copper battery, and from those batteries you can get a voltage. And so those dollar store batteries usually have a voltage of 1.10 volts. Okay, so I'm going to show you how to get the voltage right now. So if you go to the right here, the so this table is called standard reduction potentials, but we can get a lot of information from this, right? We can get the we can figure out which one is going to be the stronger reducing agent, which is our anode, and we can find out what's going to be the stronger oxidizing agent, which is our cathode. So So remember, things that are closer to the bottom end up becoming our anode. Okay, so we had, for the zinc copper battery, we looked up zinc, and we found out that it has a voltage of negative 0.76. Okay, and we looked up copper, and we found out that it has a voltage of 0.34. So these numbers here are what's called the electrical potential. They are the voltage of that half reaction. Now, oh, actually, one more thing. Before I go from here, okay, oh, I went from there. Okay. So remember, I want you to take a look at, let's get everything in shot here. Okay. I want you to take a look at some differences. So remember, we said our half reaction, our oxidation half reaction, was this. And our reduction half reaction was this. So these are called reduction potentials. This is, remember this, this chart is called the standard reduction potentials. Okay, all of these chemical reactions are written as reduction half reactions. Okay, you'll notice that we have all of the ions on the left, the metal ions on the left, and we have the solid metals on the right. Right? So they're written as reductions. Okay. When we're getting our cell potential, you'll notice that it's 0.34, positive 0.34 volts for copper, right? Which matches the table. But for zinc, okay, we have to change the sign because it's an oxidation half reaction. So basically, this reaction is happening backwards, right? We start off with the zinc and we end up with zinc 2 plus. Okay, so because oxidation is the reverse of reduction, we write the reaction in reverse and we change the sign, right? So originally this voltage was negative, but because we're doing the reaction backwards, it will become positive, right? And we'll get 1.10 volts. If you like a good old-fashioned formula, wait a minute. Right. Yes. When you have a moment, nothing urgent. Okay. Can you come and see me in the main office? Sure. Thank you. Right. If you're uncomfortable with changing the sign, you can use this formula. Okay. So this says the change in cell potential, meaning like the overall total cell potential, is equal to the reduction potential minus the oxidation potential. And those are the ones that you can just look, so you can just look it up on the table, and you could, write 0.34 minus negative 0.76, and you'll still get 1.10 volts. Okay, so you can either remember to change the sign, or you can use this formula, one of the two. Okay, either one gets you the correct answer, right? For one of them, you have to remember to change a sign. For the other one, you have to remember the formula, and you have to know what happens when you have two negatives in a row in an equation. They change to a positive. So, okay, that is how you calculate the voltage of a battery. So depending on what metals the battery is made out of and what half reactions are going on, batteries can have different voltages. Okay, so the cell potential is the measure of the potential difference across the electrodes, right? That's how we say it in physics. This is the measure of potential difference across the electrodes. It's measured in volts using a voltmeter. So if you made your own battery at home, you could get a multimeter from like Canadian Tire or any hardware store, and you could measure the potential of your cell. As the cell operates, the potential difference gradually decreases until it becomes zero. The electron flow has stopped and the cell is dead. So you can, if you have one of these multimeters at home, right, you can use it to test your batteries. You put the two electrodes, one on one end, one on the other end, and one on one end, one on the other end, and you can see what the voltage is. So if the voltage is close to, 1.10 volts, right, you know that the battery's fresh. And if it's far away, you know that the battery is dead. All right. So, worried because somebody left the meeting. Oh, there we are. So, as I was saying, okay, if you have a multimeter at home, okay, you can measure your batteries to see how fresh they are. If you have a regular battery, that is a zinc copper battery from the Dollar Store, if it's fresh, its voltage should be close to 1.10 volts. But over time, the potential difference is going to decrease as you run out of fuel in the battery, and this voltage will decrease. So it'll go down to like maybe 1.00 or like 0.95. But eventually, it's going to drop so low that your battery is going to die. It's going to become dead. So if you have a multimeter at home, you can check how fresh your batteries are. So going down here, we have an example. So we're going to practice drawing and calculating batteries. And this is going to be your last assignment in the course. Okay. So it says that we have a battery that consists of a copper strip in copper 2 nitrate and a tin strip in tin 2 chloride. So one of these strips is copper and the other one is tin. Okay, and the copper is in a solution of copper 2 nitrate. So that means it has copper 2 plus ions and it has NO3 minus ions in it. Okay, the tin strip is in a solution of tin 2 chloride. So it has tin 2 plus ions in it and it has chlorine in it. Okay, so when I connect these with a wire, what's going to happen? So in order to figure out what happens, we are going to have to figure out which metal is our anode and which metal is our cathode. Okay, so we're going to look up tin and copper, and we're going to see which one is higher and which one is lower. Right? So we have copper here. Right, here's our copper to copper 2 plus. And we need tin and tin 2 plus. That's not good. I don't see it. I see tin 2 plus to tin 4 plus, but I don't see tin to tin 2 plus. So we may need another chart. Interesting. Okay, let's see if we can find one with tin. Okay. So this reminds me that I need to check your exam to make sure that things are going well. We used this last year. So if we take a look, okay, if we take a look, we can see tin is around the middle. Well, that's annoying. It won't even let me click on it. There we go. Okay. So we can see that tin is around the middle, right there. I'll put it in the middle of your screen. Okay. And copper is, don't tell me we don't have copper. Oh, okay. No, that's copper 1 plus right here. Okay. So they're both on the screen now. So I can see that copper is higher. Copper is around the middle of the screen. Copper 2 plus 2 electrons makes copper metal. Okay, that is a so it says increasing strength of oxidizing agent, right? So copper 2 plus is going to be a strong oxidizing agent, which means it's more likely to be reduced. Okay, tin 2 plus is a weaker oxidizing agent. It's a stronger reducing agent, right? So tin as a metal is a stronger reducing agent, so it's going to be oxidized. So tin is going to be our anode, right? The lower one is going to be our anode. The higher one is going to be our cathode. This is the one I want to use. Remind me, I have to keep this, and I will upload it for you. Okay. Back we go to our okay. Yes. So where were we? we had a copper strip that I put here, Cu. We had a tin strip that I'm going to put here. Okay, the tin is going to be our anode, and the copper is going to be our cathode. The higher one becomes a cathode, the lower one becomes an anode. And I was talking about how the copper has copper 2 plus ions, right? So you have to make sure that the when you're looking at the chart, that you have both copper 2 plus and copper as a part of the equation. And the same thing with tin, you want to make sure that tin has tin 2 plus and tin metal, both of them in the equation. Okay, so we found out that tin is our anode and copper is our cathode. Copper is in a solution with copper and nitrate. Tin is in a solution with tin and chlorine. So that means, so from in your anode, okay, you're going to go from the metal to the ion. And you're going to lose electrons. At your cathode, right? So this is that I just wrote there is the anode half reaction. So it says identify which electrode is the anode. That's tin. And the cathode is copper. And we can write the half reactions. So the oxidation half reaction happens at the anode. Okay, and the reduction half reaction happens at the cathode. So the reduction half reaction starts with the ion, right? It gains electrons, so those are on the reactant side, and we end up with the metal. Okay, so our reduction half reaction starts off as an ion and ends up, oh, forgot the electrons. Okay, so when we're drawing the battery, we should show what's happening. So the tin, right? The tin will break up into the ion and the electrons. The electrons will go up because they're going to join this wire. Okay, the electrons are going to flow from the anode to the cathode, right? So just make sure that your arrows are pointing to the cathode. And then they're going to come down here. And they are going to combine with the copper ion, and they're going to turn into a copper atom. Right, and then we have to deal with the salt bridge. So the salt bridge could be any positive metal ion and any negative either non-metal ion or polyatomic ion, and it doesn't really matter. Okay, the cation or positive ion will go to the cathode, right? This and this start with the same letter for a reason, okay? And the anion or negative ion will go to the anode, right? For a reason, okay? So remember that at the anode, we're making positive ions. So we need negative ions to balance them. And at the cathode, we're removing positive ions from the solution, so we have to add positive ions to make everything balance out. Okay, so let's see if we've done this diagram well. So it says label the anode, done that. Label the cathode, done that. And the overall cell reactions, done that occur when each pair of half cells are combined to form a galvanic cell. Draw the galvanic cell for each labeling all parts and showing electron flow, right? We can see electron flow is through the wire, and showing ion flow. So I'm showing that the tin is becoming an ion. I'm showing that the copper is becoming a solid, going away from being an ion, and I'm showing the ion flow at the salt bridge. Right? So I've done my job there. So, and those are basically what you need to draw a good galvanic cell diagram. Okay, so it says write the overall redox reaction for this cell. Okay, the overall redox reaction, remember, the electrons will cancel. And if the electrons are not the same number, I'm going to need to multiply the reactions so they are. Right? In this case, I don't have to because they're the same number. So everything, I'm going to write everything before the arrows on the left-hand side of the arrows from both reactions. From the after arrow, and then we're going to do the electrical potential, right? So that's the reduction potential minus the oxidation potential, right? So let's do that, shall we? So we need to look these up in our chart. Okay, so the copper reduction potential is 0.34, and the oxidation is the tin, which is negative 0.14, right? And that's the one, okay, so. Okay, so if I'm writing it as part of the half reactions, right, I could write that E equals 0.34 here, and I would have to change the potential of the tin because it's our anode to positive 0.14, and then I could just add them down here like this, and we would get 0.48. Or if I didn't want to change the sign, right, I write the reduction potential minus the oxidation potential, and I still get 0.48, right? Volts, 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 volts. Okay, so this battery will produce 0.48 volts. I have another example on the next page, okay, where the same thing will happen. So it says label the anode, the cathode, the overall cell reactions that occur when each pair of half cells is combined to form a galvanic cell. Draw the galvanic cell for each, labeling all parts and showing the electron and ion flow. So this time I have an aluminum strip in a solution of aluminum. Aluminum, if you look it up on the periodic table, it makes an ion of Al3+, right? So, and then it says silver in a strip of silver nitrate. Okay, if you look up silver on the periodic table, it will say silver has a 1+ common ion charge. Okay, if it has more than one ion charge, it will say in the name of the solution what ion it goes to. So for example, if you have copper 2 nitrate, copper can be 1 or 2, but it tells us that in the solution, when it dissolves, it goes to 2. So I would know that the ion is copper 2. Okay, if it doesn't have the Roman numerals, you have to look it up on the periodic table. So, okay, so it says aluminum nitrate, which means that the other ion is nitrate. Okay, and then it says silver nitrate, so I know that the other ion in the solution is also nitrate. So I tried to put the metal ions next to the metals. I don't know if you know it makes it easier to show the ion flow later. So I need to figure out which one of silver or aluminum is my anode. So I'm going to go to my chart. Let's see if I have silver here. I do have silver here. And aluminum, 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 aluminum. Oh, okay. So I've put it up so that silver is at the top of my page and aluminum is second from the bottom. Okay, so silver is going to be reduced here. It's going to be my cathode because it's higher, and aluminum is going to be my anode because it is lower. Okay, so I know that aluminum is my cathode. Nope, sorry, my anode. Because it was the lower one, remember? And silver is my cathode. Okay, and that means that at my anode, I go from the metal to the ion, and I lose 2 electrons. At my cathode, I go from, from an ion to a solid. Right, and of course the charge for silver is what, like 1 plus, so I only need 1 electron. Whereas my ion for aluminum is 3 plus, so I would need 3 electrons. So my electrons right now are not matching. So I'm going to show you what to do when that happens. Okay, but before I do that, let's complete the diagram. So we know that a wire is going to connect the electrodes, and we know to draw the electron flow from the anode towards the cathode. Okay, we know at the anode we're going from a solid to an ion, right? So your arrow should point to the ion, okay? And we know it's going to split up into 3 electrons, okay? And then we know that at the cathode, it's going to go from the ion to the solid. Right, and 1 electron will join it. We know that, so we've labeled the anode, we've labeled the cathode, we've done the overall cell reactions, we've done the electron flow, we've done some of the ion flow, but we can't forget the salt bridge, okay? The salt bridge, we have positive ions, at the anode sides, so we have to make a negative ion to come down from the salt bridge. And we have positive ions being removed at the cathode side, so they need to be replaced by positive ions. So remember that the cation always goes to the cathode, and the anion always goes to the anode. Okay, so now we're going to finish this question. It says, identify which electrode is the anode and which is the cathode. So aluminum is our anode and silver is our cathode. The oxidation half reaction happens at the anode, so we're just going to put that there, and then the reduction half reaction is going to happen at the cathode. So when we write the overall redox reaction for this cell, you'll notice that no longer do the electrons line up, but that's okay. All we have to do is multiply the reduction half reaction by 3. So we would end up getting 3 silver ions plus 3 electrons makes 3 silver atoms. Okay, so now our electrons will cancel. So we would get, okay, aluminum plus 3 silver ions makes Al3 plus 3 silver atoms. Okay, now we have to calculate the reduction potential. Okay, one thing that you should know is that multiplying a reaction does not change any of the reduction potentials. So we're not going to multiply any of the potentials by 3. Okay, so we will go back and look up our, so silver is 0.80 and aluminum is negative 1.66. But remember, okay, that the sign of it will change. Right? So this will have a potential of 0.80 volts. Sorry, nope, wrong one. 0.80 volts, right? And the oxidation half reaction, instead of being negative 1.66, right, we change it so it's the other sign. And then so we'll get positive 2.46 volts. Your voltage should always be positive. If it's negative, either you've forgotten to change the sign of the oxidation half reaction, or you've actually chosen the wrong anode and cathode, right? You might have to flip the anode and cathode. If you want to use the equation, right, it's reduction minus oxidation. And then we would have 0.80 minus negative 1.66 volts. And that would give us positive 2.46 volts still. Okay, make sure you're using the voltage sign when you do your calculation. Otherwise, I will have to take part marks off, right? So our units are important because remember, we can measure things. Sometimes, like calories and joules, we don't know what unit that you intended if you don't tell us. So we have here some galvanic cell practice. says for each of the following electrochemical cells, identify the anode, the cathode, the reduced species, and the oxidized species, right? So the anode, right, we know that the anode is always, it says for learning purposes, the cathodes are not always on the left. Well, that's rude, okay? So what you're going to have to do here, okay, so they're telling us the anodes are not always on the left. They're breaking the rules. So you will have to compare these two and use the chart. Okay, I will put metals on it, right? And you're going to see which one is higher, which one is lower, right? So remember, the higher is the cathode, and the lower is the anode. And then the cathode ion is the oxidized, right? And the, sorry, no, that's wrong. The anode ion is oxidized. I don't know what's wrong with me today. The anode ion is oxidized, and the cathode ion is reduced. So then it says write half reactions, right? You can get the half reactions from the table if you want, but it's pretty easy to do without the tables. Find the net reaction, right? We might have to multiply so that the electrons are equal, and then calculate the standard cell potential. So you would need the voltages there, okay? So that's for you to practice. It says you have to make a galvanic cell that can provide as close to 1.5 volts as possible. So find some combination of anode and cathode that when you do the standard cell potential, you would get close to 1.5 volts. And then it says sketch the galvanic cells based on the following overall reactions. Show the direction of electron flow, the direction of ion migration through the salt bridge, and identify the anode and the cathode. Give the overall balanced reaction. Right? So it gives you 4 situations there. The answers for question 1 will be for the voltages for the cell potentials are here, and then so that's for you to practice on. We have the very easiest assignment you'll ever do in this course. Right? You can either print this out or do it on a plain piece of paper. I don't care. Okay. Of course. Okay. I promise you, when this shows up in Word, the picture is beneath it. So it says starting with a piece of zinc in ZnNO3 and a piece of silver in AgNO3, label the galvanic cell that results. Remember to include the anode, the cathode, the directions in which the ions move, this in the solution, the way the electrons move in the circuit, and then it says the salt bridge containing sodium nitrate and any other components, right? So you're going to fill in or draw by hand this cell. You're going to state which metal is the anode and which is the cathode. You're going to write the half reactions. You're going to write the overall redox reaction for the cell. You're going to calculate the cell potential, and you're going to try to write the galvanic cell notation for this cell, right? So that's the ones with the slashes or the pipes, right? Where you're going to have to write that notation, okay? So that's your assignment. It's very, very, very easy. I will upload a PDF too, just in case you want to do this on your computer and you don't want the picture in a stupid place. So that is going to be your very last assignment. I'm going to take a break because I have to go see what's going on at the office from when they paged me. So I will come back with a final little lesson about electrolytic cells and corrosion after the break. Probably, let's say it's 10:55 now. So 11:10 or 11:15 is when I will be back. Okay. So one more lesson and then this class is over. All right.